Thank you very much for the introduction. Good morning, everybody. Yeah, very important. I would like to thank the organizers of this intense and interesting event for the opportunity to give you a presentation about random elastic networks. So, as I already told, the interest in this topic comes from a project about random open cell foams. I was involved a couple of years ago, and the first thing I had to understand was how complex these materials actually are, because we have local material properties, we have local geometrical properties, and last but not least we have local topological properties, and all this together with randomness determines eventually the overall response of such a material. Afterwards, we had to understand that without a suitable investigation strategy, we will not be able to gain real insight in this matter in terms of uncovering underlying principles, formulating the corresponding cause-effect relations, etc. Therefore, the idea emerged to develop such an investigation strategy by means of toy problems. That's to say, problems which are as simple as possible but sufficiently complex to reflect at least important characteristics or important features of the real material. And such a toy problem is sketched here. It consists of an arrangement of m times m quadratic cells. These cells are assembled from trusses. Trusses react only on tension compression. And to every cell, exactly one diagonal is assigned. And you can think about this assignment as, for instance, a random assignment. The diagonal goes or from the lower left to the upper right, or the other way around. The advantage of such a structure is that we have easy control over, for instance, topology, which is not simple with respect to general networks. The question is now, how can we characterize such a configuration in order to distinguish between different cases? And seeing these diagonals as a discrete field on a lattice, the first characteristic, which is rather obvious, is the ratio between these two types of diagonals, which I will call in the following the 0 and the 1 diagonals. Another characteristics can be thought as a short-range two-point correlation regarding this discrete field, and it gives us a measure regarding regularity or order, if you like, in this configuration. It goes as follows. If I pick here such a cell with its diagonal, I compare the diagonal of this cell with the diagonals of the nearest neighbor cells. If we find different diagonals, this comparison evaluates to 0. If we find, to 1. If we find equal diagonals, this comparison evaluates to 0. So for this particular cell, the comparison between these diagonals gives 1. With this nearest neighbor evaluates to 0, here 1 again, and here 0 again, and we sum up the results of these comparisons. So our order measure evaluates, this is this term here in red, evaluates to 2 for this particular example. We sum up for the whole structure the results of the local order measure, and we divide it by m squared, where m is the dimension of this configuration. Our hypothesis is now that if we expose this structure to a mechanical load, where we apply here an overall strain in a periodic arrangement or with periodic boundary condition, then our hypothesis is that the strain energy of this configuration is a function of this order characteristic mu and the ratio between these two types of diagonals. In order to check our hypothesis, we need a suitable sampling strategy, because it's a combinatorial exercise to find out how many possible configurations exist. And it turns out that for m equal 20, we already have 2.6 multiplied by 10 to the power of 120 different configurations. This is not feasible. We would like to generate samples from a limited number of configurations, and of course we would like to sample according to our characteristics we defined for the network. And here we got a lot of support from colleagues from the stochastic department of the University of Freiburg. They proposed to do this sampling by means of a model which is well known in physics, which is the so-called Ising model. And its advantage is that it's described by this probability function, which gives you the probability of for a given configuration as a function of the regularity of this configuration multiplied by such a control factor beta and divided by the partition function, which just ensures that the sum of all probabilities is equal to 1. Since we do not want to control just the regularity but also the ratio between these two types of diagonals, we used a variant of the Ising model, which is called Ising model with fixed magnetization. And we can sample now by means of this model in combination with an algorithm which is called Metropolis Algorithm, configurations according to our characteristics. And the results of this investigation you see here. The results given here are for the case that we impose an overall shear deformation together with periodic boundary conditions. In this graph, the strain energy or specific strain energy is plotted for different configuration, and the configurations are characterized by the ratio of 0 and 1 diagonals and the control parameter of the Ising model. Since for the mechanical response it doesn't matter if you have 30% of these diagonals and 70% of the others, or the other way around, we use a modified ratio of these diagonals. If we demand that the row bar is 0, then this means that all diagonals point in the same direction. And these are all these structure here, so the control parameter of this Ising model doesn't have any influence. And you see here a representative of these structures which is completely regular. On the other hand, if we choose a beta equal -1, we get this repulsion effect. So we generate structures where we have an alternating direction of these diagonals. These structures are also completely regular. The other structures here are more or less disordered. A very interesting case is this case here for row bar equal 0.5 and demanding a very ordered structure. So beta equal 1 means actually that we demand to find very ordered structures. If we demand at the same time that we would like to have half diagonals of this direction and the other half of the other direction, the only possibility to achieve this is clustering. What you see here is a typical representative, and let's say the structure which fulfills this criteria best is a structure where all the diagonals point in the same direction. Then you take half of it, and those structures belong individually to the strongest structures. Because what I didn't tell you is that for displacement control, high strain energy means high stiffness. Huh? So you take this structure, you divide it in two, both parts belong to the strongest configuration, you put them together in the wrong way and you get the weakest configuration you can achieve. Another result was that if you now randomize for instance, the coordinates of the nodes, so you do a geometrical variation, that all the results are below this curve shown here. So what this curve actually shows is that there is a correlation between these two characteristics and the mechanical response of this type of networks. However, this beta is actually a control parameter of a model. It is not really a characteristic. On the other hand, there is a nonlinear relation between this beta and these order characteristics mu. Therefore, we can plot our results as functions of genuine characteristics, yeah? Not as function of a model parameter. This is possible. The next step would be to transfer these results, or to plot these results as function of genuine network parameters, because general networks do not know this regular background structure. I will come back to this point a little bit later. So these results are published already together with two colleagues, as I mentioned already before, from Technical University Freiberg, from the stochastic department. And now the question was, how can we proceed? And the next step was to ask what happens if we at the same time vary the material characteristics in this network. We apply a similar scheme, considering exclusively at the moment the diagonal trusses, defining a ground stiffness, so to say, lambda naught, and two possible variations. We can or rest from this stiffness a delta lambda, or we can add to this stiffness a delta lambda. So we have three possible states regarding the material properties of the diagonals, which is here sketched by these colored dots. In addition, we define the ratio of those diagonals with respect to the dimension of the structure, or the total number of all diagonal rods for which the stiffness is the given lambda naught without any variation. And in the same fashion as before, we can define this nearest neighbor correlation, or this order measure, if you like, again locally, and the global value we obtain by summing up all these local results and dividing by m squared. Our hypothesis is now that for a given loading, for instance an overall shear strain, that the mechanical response in terms of strain energy depends now on the order measure regarding the direction of the diagonals, the ratio between these two types of diagonals, and in addition the order measure with respect to the material properties and the number, or the relative number, of non-altered diagonals. Now, in the Ising model we only have two states. Here we have three, but there is already a model in physics which accounts for that. This is the so-called Potts model for three states. The methodology we apply to sample our configurations according to our characteristics is more or less the same. And what you see here is reflect part of the results. The picture here in the center is the picture you already saw before, when we only vary the direction of the diagonals in this structure. And now we take out one of these configurations, for instance this one, and vary in addition the material properties. And this we can do for every given rho bar and beta. And what we see is that here as well we find a correlation between that. So this actually justifies our hypothesis. What we can say in addition is that for all these configurations, the relative difference between the maximum strain energy and the lowest value for the strain energy you get depends quadratically on the contrast you apply, which means this delta lambda. With respect to the transition to general network, unfortunately at the moment the only thing I can show you is what does not work. As I already mentioned, general networks, for instance networks you generate by Delaunay triangulation, they do not know, they do not have these nice quadratic background, the cell background structure. To characterize this kind of networks, proper characteristics are, for instance, the variance in node degree, where node degree means how many trusses are connected by one node, and a directional measure which is defined by the quotient of the sum of the sinus, of the diagonals divided by the sum of the cosinus of the diagonals. And this measure works actually quite well when we do not talk about the variation in material properties, but as you see here, if I multiply this with the corresponding stiffnesses of the trusses, the picture we get is actually worthless. So at this point we still have to work on this transition from our results for these idealized structures to general network characteristics. So to sum up, the interplay between topological geometrical characteristics and material properties is rather complex. The strategy we applied for varying the material properties should be extended to incorporate also the horizontal and the vertical rods. The result, strain energy as a function of the ratio of diagonals and the regularity of these networks, is seemingly a kind of upper bound, but there is still no proof for that. Of course, it would be nice to switch from this discrete sampling of material properties to a continuous sampling. However, at the moment, I don't know exactly how to do that. Eventually, we are looking for a continuum description. In parallel, what we do actually right now is we would like to do the step from this kind of structures to structures which are closer to our original problem, which means random open cell foams. For this purpose, we try to generate, or we generate structures according to the same principle. Now we define a network made from m times m quadratic cells, but now these cells are assembled from beams. And at the moment we are using classical Euler beam theory. We assign again a kind of diagonal to every cell and connect the end points of these diagonals with corresponding midpoints of the horizontal, respectively vertical edges. So this way we can generate structures assembled from two types of convex cells, where we find cells with 2 edges, with 4 edges, respectively cells with 5 edges, arranged in this network. And the first result you see here, again the strain energy for such a structure exposed to compression. The simulations were done with structures of a dimension of 25 by 25. I show here only the pictures for 15 by 15 because otherwise you don't see very well what's going on in the structures. We have 4 more scatter here, but at the moment I attribute this scatter to the lack of periodic boundary conditions. This is still missing in the implementation. We can see that there is again a correlation between the mechanical response and these characteristics, where we use the very same characteristics as we used before for these simple truss networks. But the correlation changes in a certain way. You find here again, I have to orient myself. This is the configuration again for the control parameter of the Ising model -1, which leads to this repulsion effect. So we have alternating diagonals here, and this gives us this kind of structures. We find again the half-half structures here, so where we define, okay, we would like to have 50% of one type of diagonal, 50% of the other, but a very ordered structure. And you see here that the results indicate that in this case, these are no longer the weakest structures. Now the correlation is in a certain way different. And the completely ordered structures you find here, and in between you find these structures which show a certain degree of disorder. And in this work, the students mentioned here on the slides were involved or are involved right now. Thank you very much for your attention.
Questions? Start with me.
Exactly in that example, is it a coincidence that you have roughly the same size of your cells, and such that in each cell you have 5 trusses, right?
No, this here.
In the original one, if you start with your foam, do you have the same foam size in each cell? Right there. What you are
this?
Yeah, the lower one.
The lower one.
So why do you have the same size of each foam?
Of each cell, you mean?
Yeah, cell of the foam, not the cell that you introduced.
Yes, at the moment, yes.
Okay.
They are all. You have only 2 types of cells. One with 5 vertexes, one with 4, and all with 4 and all with 5 have equal size. That's a choice we made. We could change that by varying, for instance, the endpoints of the diagonals.
I should ask a question as the chairman.
Oh, you don't have to.
But it's too early.
I know there is one. I would say there is one.
So finally, this structure is the second one is very close to periodic, but not periodic. It's can be considered as pseudo-periodic. This one or not?
This one?
No, on the left.
This one?
Yes. At the end, it will never be periodic, but it's very close to be periodic.
But this actually depends what kind on the parameter you choose. Of course, if you choose this configuration where you have this repulsion effect, of course it's periodic. If the structure is completely regular, then it's also periodic. But these are only the limit cases. So everything else here in between won't be periodic. But on the other hand, it comes more to isotropy. Because of the irregularity. Periodicity we apply but for the whole configuration. So we imagine a material assembled from a periodic arrangement of this bigger configuration, so to say. And our problem is actually that we try to understand how this interplay between geometry, topology, and randomness affects our response.
And on the graphic here, it seems that there is some main grooves, but also some points that are fully out of the grooves.
Yeah.
How do you explain that?
At the moment, I explain it, or I try to explain it, first of all, by the lack of periodic boundary conditions. We use periodic boundary conditions, full periodic boundary conditions, for the simpler truss structures. Here we are actually in the implementation stage, so the periodic boundary conditions are still not implemented. This is one reason. The other reason is you can consider these cases even without periodic boundary conditions, but then you have to make your structure far bigger in order to get rid of the boundary effects. I tried, I think the limit right now is 35 by 35. Then computer is out of memory, so to say. So this is a step we have to do next to incorporate periodic boundary condition. And then I hope that we get a picture as nice as for the simpler structures, where you saw that here it's a very good match. It's still not, it's not perfect with respect to this fit function, but you can improve the fit function, which is actually, I forgot to mention, this grid you see here together with the points is actually a fit function we plotted here, so you can improve this as well. But you're completely right. I mean, here we still have to work on that.
So did you consider the RV size basically of this case? By changing by
yeah. For the truss structures we did. For the beam structures here, not in a systematic way. So we try 10 by 10, 15 by 15, and then we check how the results change, especially for the complete disordered structure. There we expect the highest scatter. So we pick a configuration with beta equals 0, which is complete disorder, and half-half diagonals, and then we check configuration size per configuration size until we reach a limit where we can say, okay, the results with configurations bigger than that won't change. That's more or less the philosophy.
Very last question. Your beams are for large dimensions?
Not yet. No. It's Euler-Bernoulli. But yeah, then these all steps are already indicated. So Euler-Bernoulli, Timoshenko, then large deformations. So.
Okay. Thank you again.